Biological systems evolved under conditions of extreme environmental volatility, relying on massive external stressors to regulate internal function. Modern longevity protocols attempt the exact opposite. They try to impose an unbroken, sterile homeostatic continuity, aiming to preserve tissues through constant, low-level maintenance. That strategy ignores the physical limits of biology. The precision of cellular repair is governed by the thermodynamic uncertainty relation, or TUR. The TUR dictates that high-precision error correction is not free. It is purchased directly through massive metabolic dissipation. Over time, the constant output of metabolic energy generates microscopic thermodynamic noise. The system eventually hits an information bottleneck. The continuous, low-level repair signals sent by traditional anti-aging protocols get swallowed by a rising static floor known as accumulated entropy generation, or AEG. Biological age is entirely defined by this AEG threshold. It represents an intrinsic material limit of structural integrity, a point where the noise is so loud the cell can no longer hear the instructions to fix itself. To survive this high-entropy environment, damaged senescent cells abandon efficiency. They adopt a rigid, highly glycolytic state, consuming massive amounts of fuel to sustain the senescence-associated secretory phenotype, or SASP. The SASP is the heavy, toxic secretory load of inflammatory proteins that aging cells continuously pump into surrounding tissue. Systemic rejuvenation is therefore a thermodynamic problem, not a biological clock. Constant mild hormesis, like daily exercise or slight caloric restriction, lacks the energetic amplitude required to push these dysfunctional cells past their AEG threshold. Chronic maintenance strategies fail because they are attempting to gently repair a structure that needs to be demolished. This radar chart maps the biological profile of a healthy cell against a senescent cell. Look at the red polygon representing the senescent state. It demonstrates a near-total deficit in metabolic plasticity, accompanied by a massive spike in resistance to apoptosis, or programmed cell death. This metabolic rigidity means the cell is permanently addicted to aerobic glycolysis and glutamine. It has lost the ability to pivot its fuel sources, locking its survival to a constant influx of heavy nutrients. Here we see the mathematical solution for cellular reorganization, the signal-to-noise ratio, or SNR. In the context of biology, this equation models the fidelity of a rejuvenation signal against the background noise of cellular entropy. To trigger a systemic reset, you must maximize the SNR. That requires an extreme gap between the body's baseline state, represented here as mu sensitization, and the adaptive stress signal, represented as mu stress. The stagnant starvation building, or SSB protocol, engineers this extreme gap. Before initiating an acute, targeted bioenergetic collapse, we must first intentionally crash the biological stress baseline. Functional rejuvenation relies on building this massive signal-to-noise ratio. By engineering an overwhelming differential between stress and rest, the protocol executes a systemic informational reset, officially abandoning the dogma of homeostatic continuity. Look at Phase 1 on this timeline. Anabolic sensitization. Over 28 days, the red stress line flatlines near zero, while the blue anabolic signal sustains at 80%. This deliberate sedentary behavior and unrestricted feeding induces exposure-related malnutrition, suppressing cellular debris clearance. Clinical validation for successful sensitization is tracked via the GDF-15 waking response. GDF-15 is a stress-responsive cytokine that indicates mitochondrial flexibility. A healthy system shows a robust morning peak, followed by a sharp decline. Phase 1 aims for a blunted, flattened response, confirming the systemic loss of mitochondrial resilience. Excess tryptophan floods the IDO enzyme, causing it to stall completely and halting metabolic shifting. Following this, metyl-3-driven hypermethylation acts as a padlock, repressing fatty acid oxidation. This locks the senescent cell out of fuel flexibility, tethering its survival entirely to continuous glucose availability. Phase 1 manipulates the denominator of the SNR equation. By driving baseline stress to zero, it tricks dysfunctional cells into abandoning their adaptive plasticity, priming them for targeted destruction. Focus on the graph's center, Phase 2, the starvation phase. Calorie cessation drops the anabolic signal to 0, while stress spikes to 95%. This extreme vertical spike triggers differential stress resistance, forcing healthy cells into a protected state, while leaving abnormal cells completely vulnerable. Healthy cells adapt immediately. Responding to sudden starvation, they activate ketogenesis and upregulate autophagy, rapidly shrinking to recycle survival substrates in a process called shielding. Trapped senescent cells cannot deploy this shielding mechanism. Their epitranscriptomic walks prevent ketogenesis, and the sudden removal of glucose throws them into immediate bioenergetic bankruptcy. To survive, rigid cells rely on the HK2 VDAC mitochondrial shield, where hexokinase 2 acts as a physical brace blocking apoptosis. The protocol shatters this brace through force. Fasting's energetic crisis and massive reactive oxygen species spikes from targeted training violently break the bond. Senescent cells also attempt to resist death via VATPase clearance. VATPase is an enzyme complex that pumps protons to regulate lysosomal pH and clear damaged mitochondria. However, the extreme metabolic workload of thermal shock and high-intensity interval training during this phase completely overwhelms this lysosomal quality control. Phase 2 weaponizes the rigid cell's own glycolysis addiction against it. By injecting extreme energetic volatility into a trapped system, the protocol forces selective apoptosis, destroying damaged populations without harming plastic, healthy tissue. To ensure complete clearance, the protocol layers a secondary mechanical stressor designed to bypass metabolic resistance entirely: pressure-induced senolysis. Intermittent hypobaric pressure targets inflexible senescent membranes. Pressure shifts trigger TMEM59 channels, flooding the cell with calcium ions that cleave structural LAMP2 proteins. The resulting fatal lysosomal rupture digests the cell from the inside out, finalizing targeted clearance. Purge efficiency is confirmed via a strict clinical biomarker, the glucose-ketone index. The protocol targets a drop into the 1.0 to 2.0 maximum purge zone. Secondary monitoring uses heart rate variability, specifically RMSSD and SDNN metrics. These measure vagal tone and autonomic flexibility, serving as a real-time proxy for the nervous system successfully transitioning out of a locked-in state and into adaptive plasticity. Final validation of the purge is confirmed by the silencing of the CJAS-STING pathway. CJAS-STING is a cellular mechanism that detects cytoplasmic DNA fragments from damaged cells, driving chronic inflaming. These metrics prove that thermodynamic noise floor has been physically destroyed. Dysfunctional tissue is completely gone, creating the precise structural void necessary for high-fidelity regeneration. Entering Phase 3, the building phase. Clearing dead tissue is useless if repopulation introduces errors. Notice the blue anabolic signal rocketing to 90% while stress drops. This intense rebound requires a precise nutritional threshold of over 3 grams of leucine. Crossing this leucine threshold violently upregulates mTORC1, the master protein complex coordinating cell growth. This drives polyamine metabolism to maximize protein synthesis. This hyperanabolic state forces stem cells to execute symmetric stem cell division, rapidly yielding 2 identical, pristine cells with 0 error transfer. This mechanism exponentially reduces the accumulation of mutations while repopulating the purged niches. This engineered growth phase allows the biological system to rebuild its foundational architecture from a clean slate without generating the thermodynamic noise of structural aging. During this rapid cellular expansion, the building phase employs a process of xeno-like monitoring. Through continuous, irreversible metabolic correction cycles, the system actively suppresses the quantum informational floor. This constant monitoring permanently locks in the new, error-free cellular architecture. This state is defined as epigenetic resonance, the optimal condition where extreme metabolic oscillations successfully entrain the genome back into a youthful, highly plastic configuration. The traditional longevity paradigm relies on chasing homeostatic equilibrium. By attempting to avoid damage, it mathematically guarantees thermodynamic failure as entropy slowly outpaces repair. The SSB protocol utilizes the inescapable physics of entropy. It resets structural integrity by intentionally oscillating between extreme cellular collapse and explosive, highly structured regrowth. To maintain genomic fidelity and functional rejuvenation, we must restore the extreme biophysical volatility of our evolutionary origins. Health is not sustained through unbroken balance. It is built by engineering the vital rhythms of feast, famine, and struggle.